GM, everyone. Hi. Welcome to today's workshop. My headphone is falling out of my ear. Hi, everyone. So great to have you. Today we will learn about Olas autonomous AI agents. And I just realized I don't have the right slides here. Let me just exchange that very quickly because these are slides from last week. So very good. We are so early, almost no, but oh, already a few people. Okay, nice. Okay, let's go. Hi everyone. I'm very excited to have all of you here today. This is, oh, I did, wait, this should be, let me remove this and then this. And then let's try this. Hi. I hope everybody has an amazing hackathon so far. And I have the right slides for you today. So welcome everybody. So great to have you. Today we will have David here to talk more about autonomous agents and how to modify them. And yeah, as always, I will give a very quick intro into what is Celo, what is MiniPay, and the hackathon, and then we will dive right into the workshop. So yeah, this workshop is part of a hackathon, just for everybody who joined from Twitter. But you will just learn a lot about Olas autonomous agents, and I will start with our main purpose of Celo, which is that we are building with purpose and building for all. And here you can also see the prosperity for all, wearing that shirt today. So yeah, why, for everybody who is new to Celo, why build on Celo and what is Celo? Celo is an EVM layer 1, EVM compatible layer 1 blockchain, and it is optimized for mobile first. That is like for everybody who knows, all the addresses are mapped to phone numbers, so even the whole infrastructure is mobile first, and we have very low transaction fees, like 0.001 USD. And one very special thing about the Celo blockchain that is, I think you can't find somewhere else, is that you can pay transactions in stable coins. So stable coins means that this is tokens pegged to fiat currencies like the dollar or euros, but and so far we have stable Celo specific stable coins like CUSD, C Euro, and C Real. We will have more soon, but also USDC and USDT just deployed on Celo, and also the proposal for using USDT as gas fees just went through, so that is very exciting. And also, why build on Celo? Because we want you to build for MiniPay. MiniPay is a stablecoin lightweight wallet. It's only 2 megabyte, and it is integrated in the Opera mini browser. It has a bit different feel than the wallets you're used to normally, because it has very like Opera was focusing on creating a very like Web2 experience for everyone. And when they created this wallet, and as this like Web2 experience this Web2 experience includes that the gas fees are paid in stablecoin, so you wouldn't pay them in the Celo native currency Celo, but they are paid in CUSD, and also the whole design is very like works with fiat currencies. The great thing about building for MiniPay is that you have, through MiniPay being implemented into the Opera mini browser, which is has a distribution of or user number of 80 million people, you will get access to this kind of distribution network, right? So first of all, huge distribution network, and second of all, seamless user experience. A lot of Web3 projects are not that far, I think, with creating this experience for non-Web3 native users, but MiniPay is very focused on that, and we want you to build for that. And yeah, also very important in MiniPay, you have, it's like any other wallet that you have like with MetaMask, but you create it just with your phone number and your email address, and you can just send to email your contacts in your phone. So it's much more usable than any browser wallet that you are used to through your desktop. And the best and most exciting thing is like MiniPay is the fastest growing wallet and already has 2 million users, which is I think very, very exciting for everybody who is building for MiniPay to getting access to more than 2 million users. I'm seeing all our favorite developers joining. Hi, Blessing. So I'm talking about Celo, I'm talking about MiniPay, and you should build, and I actually have the perfect opportunity for you to be building, and that is the Build with AI Transforming Personal Finance Hackathon. It started on the 5th of April, it will end next Monday, but if you want to join, applications are still open. Just scan this QR code. You still have a whole weekend and like almost like a week to build, so why not? I feel like most hackathon teams build most in the last week, so I think you're not too late if you're going to sign up now. Just an overview, there's a 10K prize pool for the fast track, which is Built with AI, Build Smart Personal Finance with Olas, which we're going to have our workshop on today. The prize pool is 3K in total, 2K for using the AI agent, and 1K for using the Olas Mac. And building for MiniPay has in total a prize pool of 7K. And again, scan the QR code in case you haven't signed up yet. Also, for everybody who has been joining all of these workshops and is building, make sure you signed up for the hackathon. I know some people that attended all the workshops haven't signed up yet. Make sure you sign up so you can get all the updates and invitations to all the events, and like you get support and help, because we also provide mentorship for all the teams. So please make sure that you're signed up and you're in the loop on all the support we offer and provide. Just an overview about the schedule. We are now on the 16th. It's our last workshop that we're hosting. It's Built with AI Agents. And tomorrow is our last event in total before this is closing. We have our second milestone check-in. Make sure you will receive an email tonight, so make sure you fill all the information in so we can support you and help you in building the best hackathon project possible. 21st is submissions. And also for everybody who is in Nigeria, in Kenya, and Uganda, there will be, Nigeria might have happened already, but I know Kenya and Uganda, the code gems will happen this weekend on the 20th. So if you are in Nairobi and in Kampala, I think, then check out the code gems and get feedback from the mentors on your pitch and on your project. But yeah, now I talked enough, and I want to invite David to the stage. David is a developer for Valerie, and which is a core contributor to Olas, and he has already hosted an amazing workshop on using the Olas Mac, which is kind of like the AI toolings that they offer. And you should definitely also check out that recording. I will share the link in a second with you. And now we're happy to have you back and hosting this workshop for all of us. Thank you so much for being here today.
Thank you for having me again, Lena. Very nice to be here again. All right, then maybe I think we can kick it off already. So as I was saying, last week we were talking about mechs and how mech agents can serve as a brain for your application when you don't want to actually implement different APIs for different LLMs out there and other services. And today we are focusing on the agent service. So basically the piece of software that actually consume all these other services. And note that I am talking about agent services and not just agents. We sometimes use just agent for short, and you have been for sure hearing about agents everywhere for the last months. But there's an important differences when it comes to Olas architectures, and this is what I want to talk just a few minutes before we start. So when you think of an agent, we usually think of this small bot that does something out there for you, right? But from an Olas perspective, an agent service is an off-chain, and this is a very important thing to notice, as not many people seem to realize that this is an off-chain service which runs as a multi-agent system. So this is not strictly true, and in fact today we will focusing on just that single agent system. But the idea behind Olas is that you can implement your services in a way that it's run by multiple parties, where every party is running at least one or more agents, and all these agents coordinate in order to achieve their goals. All right. So these agents can basically do any complex processing, and they reach agreement on what the next action that they need to take is. And the good part of this being a multi-agent service usually is that they can run continuously, even if some of the agents are down, so on and so on. And also different parties can run this in a decentralized ways, because of course every party can run 1 to n agents, so they own a part of this, let's say, small mini chain of agents doing things, right? And we don't have, unfortunately, we don't have enough time to talk about how this works, but I think I can show you just a glimpse on what an agent service architecture looks like. So, Elena, let me know if this is not big enough for the screen. I think it should work. So basically, okay, perfect. So this is an agent service. As you can see inside the purple line box, there's different operators. Let's say I am one operator, Lena can be operator 2, and one of you can be other operators in this room, and each of us can run a different agent. These agents can run the same code or a different code depending on what the needs are for our service. Let's simplify today and think that everyone's running the exact same agent. So all the agents implement their business logic in what we call the FSM app, and I will cover this after the demo. This is a little bit more technical, but the important thing here is that you remember that there's like two main logical parts inside an agent. One is the FSM app that implements the business logic, so that's the code that implements what the agent actually does. And then there's the consensus gadget node. This is a separate part of the agent that is responsible for communicating with the other agents and form a mini blockchain where all the agents share what their thoughts are, what their actions are, and they reach consensus on what the next step on their execution is. So let's say, for example, that an agent service wants to perform a swap or a transaction, and it transfer anything on chain. But remember that this is not limited to the chain. This is why we have this little cloud here. This goes through the internet. This can communicate not only with blockchain 1, blockchain 2. This is chain agnostic, all right? We can communicate with different blockchains at the same time, but we can also communicate and transact with traditional services like Twitter or any Web3 approach, like databases, anything that you can come up with, you can do. So let's say, as I was saying, that this agent service want to send a transaction to this blockchain one. So as I was saying, all the agents need to reach consensus for this to happen. And this happens through safe multisig. So for all of you that are not aware of what this is, there's this smart accounts called safe wallets that are not controlled by a single private key, as we usually see with AOAs. This is a smart account that is deployed on chain, and transactions can only happen there if at least a number of signers approve that transaction. So in this case, let's say we want to transact with, send some funds there. So if we are 4 different agents, let's see, for simplification, at least 3 of them, it usually is, this is configurable, but usually is 2/3 of the agents plus 1. So 3 out of the 4 agents need to sign a transaction before that transaction can really happen. So this transaction travels to the safe. The safe checks and verifies that all the signatures are valid and they are enough for the transaction to happen, and then the transaction goes through. This is important to remember because we will deploy in our own safe for today's demo, and this is the reason why we need it. Okay, so this is the overall architecture, and I think now we can talk about what the agent that we are using in today's demo is doing. So maybe some of you already remember what we were working on last week. We prepared this MEC tool to convert and transform natural language where a user specified like a transaction in natural language, saying something like, I want to send 10-way to this address, and then this sentence is automatically converted into a transaction that it can be signed by the agent and then settled. So the flow here is something like this. The user, as I was saying, sends a request using natural language. This is an HTTP request that goes to the trader agent that we will be running and demoing today. And the agent receives this request and realizes that he needs to make a MEC request to get the actual transaction data. So it prepares a MEC request and writes it to the Celo chain. We have another agent, which is the MEC agent, that is always listening for this kind of request. So the MEC agent pulls the request from the chain, does some preparations. This request includes some data like, this is the tool I want you to use, this is the prompt I want you to use. So the agent prepares this tool and realizes it needs to use, in this case, OpenAI APIs. So it sends a request to OpenAI servers, it gets a response back, writes this response to the Celo chain, and then our agent will be listening for these responses. We'll get a chain event from a specific smart contract that is deployed there, and it will finally receive the response from the MEC. The response for the MEC is an already prepared transaction that the agent can sign and already send to the Celo chain, so the transfer would be complete. So if you have been paying attention, you will see that there's 5 different transactions happening here for a single user request. One is the actual, the first one is the agent request. Sorry, three of them, not 5. One is the MEC request, another is the MEC response, and finally we have the transfer, right? So we have prepared this repository here. You can find the link in the hackathon site, and we have prepared some README that with specific detailed instructions on how to run it, and that's what I'm going to do now. Let me open my terminal. The first thing you need to know and to prepare before you run this agent is that there are a bunch of requirements for this to run on your computer, right? So first of all, you will need to be you need to have Python at least 3.10 installed in your computer. You need to install Tendermint as well. As I was saying, Tendermint is the what we are using for consensus gadget at the moment. So that's all the agents will need to use that to communicate with each other and reach consensus on the transactions. You need to install IPFS node. I know there's a lot of things that are to be installed here with, and we have linked with the instructions there. You need pip, poetry, Docker engine, and Docker compose. And you need to verify that you can run Docker without the need for being a root user. If you follow this link, you will find some instructions on how to do that. Easy way to verify that you are or your permissions are correctly set is to run Docker run hello world. If that runs, you are good to go. So, all right, I'm going to do this on a temporary directory. So the first thing I want to do is to clone this repository. I'm cloning it. Okay, I have my repository clone now. I am going inside it. Next thing is to enter and create and enter my virtual environment, and also install all the package requirements. Okay, I think that's already there. Next thing is, whenever you are running an agent, let me share the repository again. You will see this packages folder here, specifically this packages.json. There's a lot of agent packages that every agent uses. Some of them are these were similar to when you use pip or poetry. You specify some packages that you are developing yourself. In this case, these are the 4 packages I developed for these services, but this service I also use a lot of other packages that are already there. So I now want to download these third-party packages, and for that, I will run autonomy packages sync update packages. All these packages live on IPFS. So what is happening now is all these packages are being downloaded and now are ready to be used. The next thing is that we need to prepare some private keys for our agent to be able to make transactions. There's this command here that you can use. You can, of course, use your own keys if you have some funds on some MetaMask wallet, for example. You can export your private key, and you can prepare a JSON file called keys.json, and this is what it looks like. It's just basically a list with, in this case, one instance, because we are running just one agent today, that includes the private and public key. These are some dummy keys that are just for the I mean, they do not have any funds there. But if you don't have any and you want to create one, you can run autonomy generate key Ethereum -n1, and then you can see that some keys.json file is created for you, and this is what it contains: the public key, the private key, and now it's time to send some funds to this address. In my case, I already have some keys with some funds there prepared, so I won't do that, but this is just a matter of sending from MetaMask or the wallet you use. The other thing we need is to deploy a safe, as I was saying before. When you mint a service through the Olas protocol, the safe is automatically deployed for you, but in this case, I will be doing so manually. So the thing is, you can visit this safe site. Looks like this. You connect your wallet and you click on create account. When you create an account, you select which chain are you deploying your safe to. In my case, this will be Celo. I will continue, and then in that already detects my connected account and sets it as one of the signers. What you need to do here is to copy the public key of your agent and paste it here. So your agent is also a signer of your safe account. And then you should specify, in this case, we can go with a threshold of just one signer. So yeah, the agent itself is enough to make transactions, right? We now go to next and we click on create. you are prompted to pay a very small fee for deploying this safe. But in my case, have already deployed one. So I'm going to go already to the repository since I don't need to deploy it. Next thing is to prepare some environment variables. We have prepared this for you, this sample.m file that includes several environment variables. The only ones you need to take care of is all participants. Here you need to specify your agent address. This is a list of all the participants in this service that are allowed to participate in it. So in this case, you only need to put your public address here. Then you will need an Ethereum Ledger RPC. Even if this runs on Celo, the Celo RPC is already pre-filled in, but you should also add an Ethereum one, because this is how Olas agents work. Usually do some verifications on chain on mainnet. You should also fill in your safe address here, and then the rest is already pre-filled for you. This is the tool that we will be using, but if at some point you develop your own tool, you can modify this native transfer one to use your own Mac tool. And the last variable I want to talk about is mass transfer value way. So for this example, I created like a security measure just in case we have some LLM malfunction or something like that. Let's say, for example, I want to transfer one way or one Celo, and for some reason the output of the LLM, LLMs are not deterministic. If for some reason it sends back like a crazy number, like send 1 million Celo, okay, this is the max amount of way this service is allowed to transfer. If you set this to 0, this basically will be not used. In my case, I set this to 1 to the 18th way. So 1 Celo is the max amount of Celo I will let this agent transfer. And I think with that, the only last thing to do before running the agent is to check that Docker is running. If you are on other operative system like Mac, you want to verify that you are running the desktop app. In my case, I run Docker or Docker info, and I can see that everything is there. And that's it. Now, this is the other repository. This is a clone I have prepared with the actual pre-funded keys. Last thing we want to do is to run the agent script that will build the agent, and it will create two different Docker images, the Docker containers. One is the agent, one is the Tendermint node that the agent will use for consensus. The first time you run this, it will take maybe 2 to 3 minutes to build, depending on your computer. Since I have been testing this before, this has been already built. So now this agent is already running. Let's go into another terminal and look at the logs. So Docker logs follow, paste the agent name. So let me make this a little bit bigger. So the agent is now running. The first thing you see is a lot of packages that the agent is using. This is not very important for now. It starts an HTTP server, lots of things that are not relevant for the demo, but you will see that at some point, the agent synchronizes with Tendermint and start running right away. I will cover a little bit more of this in a second, but what the agent does is go through a series of steps. Like first, it will check if it has some user request, and if not, it will reset itself, and that's when you see these messages that say period end. And the agent will be running in a loop until it has and listens for a user request. So now I am going to send a request to the agent. Request looks like this. This is an HTTP request. I am using curl for this. So this is a post request. I'm calling the localhost 8000 endpoint, which is where the agent is listening to, and specify some JSON header. And this is the important part. This is what I am actually sending to the agent. this is a JSON object that just includes the prompt I want to use for it to run. Please transfer. For example, I can say 0.001. I can use way or Celo. For example, let's use way here and use like, I don't know, 10 way, and I will send this to one of my addresses, which is this one. So I'm sending this. I receive an OK response. And now let's look at the logs. Here we see that the agent has received an HTTP request with the prompt I sent. So the agent prepares first the MEC request. Here it says processing MEC request. It's preparing some metadata. This is what we covered last week on what the MEC request looks like. All the prompt, everything is stored to IPFS and then written to the smart contract. This is turned into a transaction. So the agent signs the transaction and it's sent for mining to the chain. This is one important thing. You will see messages like this whenever you have several agents. One of them is responsible for sending the transaction. That's why you see this, I am the designated sender attempting to send the transaction. When you run with multiple agent services, which is not the case today, agents take turns and try to send the transaction until the transaction succeeds. So there's a lot of transaction data here that we can basically forget about. And now the transaction should be okay, I had some issue here. All right, the transaction has been sent and now the agent is waiting for a MEC response. Let me scroll a lot. You could see some errors when the RPC does not return a valid response, but at some point you will see that you will see a message that says a transaction, a MEC response has been received. And here it is, received the MEC response, and the MEC response in this case is a JSON object that says, okay, this is the transaction you should send. The agent got this and used that JSON object to prepare another transaction. This is the third transaction and sends to the chain. This is a lot of nonsense data. So let's go to Celoscan and see what happened there. So first, let me refresh. This is my agent's address, and you can see that there's two transactions on the last few minutes. The first one was the MEC request. If I open it, you can see that there's some logs there. The important thing here that there's a request here. This is a MEC request. Then if you go to the second transaction, this is the actual transfer transaction that was sent to the safe. If I go to the safe address, same thing. You see it here two transactions, because remember, all transactions that the agent does go through the safe, and the important one is the last one. Let's go through it, and we can see that this transaction has managed to transfer 10 way from the safe to the address of the agent, which is the address that I told the safe to send the funds to. So now the agent finished making the transaction and started again looping, listening for other user requests. Now I think the demo is over. So I'm going to kill the agent with Ctrl+C, and we can go through what the agent actually looks like. And for that, I want to cover a last piece from our docs that I mentioned before, which is FSM maps. So whenever you design an agent, you don't need to actually know this, but it's important for a bit of context. So whenever you design an agent, you need to remember that most of our services run as multi-agents. Not in this demo, but usually they do. And even if there are single agent services, maybe at some point you want to decentralize this so multiple parties can run the service, right? So you design all your business logic split in different modules or steps that we call rounds. So agents can first run step 1 and then go through a consensus round before going to step 2. This is how we keep all the agents in sync. So we go from state 1, all the agents run state 1, they reach consensus, everyone agrees, or at least a threshold of agents agree, then go to state B or C or D or whatever. So this kind of diagram is the important thing to have in mind whenever you design an agent. So when we designed the agent that I showcased in this demo, this is what the FSM map looks like. In this case, the important boxes are the blue boxes. These are the boxes that I implemented for this service. The other ones were already off the shelf, implemented by other Valory engineers, and anyone can basically reuse them. These are some of these packages that I showed before in the repository. When I show these third-party packages, these make up these boxes. So how this agent works? When I started the agent, the first thing we saw is that the agent synchronized with Tendermint, and in this case there was only one agent, but if there was many more, they would go through a registration stage where they connect to each other to form this mini blockchain. They share their configurations, they share some data, and once registration finishes, they can start running. Then we have this decision-making blue box, which is the brain of this agent today, where all the decisions are made, right? So do we have a user request? Do we need to make a Mac request? Do we need to set that transaction? All this happens here, and I will show the code in a minute. So the happy flow here, what we showed on the demo, is that there's this HTTP handler that is part of the agent as well. This HTTP handler receives the user requests and sends the request to the decision making. So the decision making is constantly looping until it has some request. Looping means that whenever it does not detect that there's any user request, it goes to reset and pause, which is only one of other these rounds that we have there, and basically is resetting constantly until it has an HTTP request. Then once it detects the first request, it realizes it needs to prepare a Mac request, so it transitions to this other module, which is called Mac Interact. Remember that we call these rounds, so this is the word I will be using from now on, rounds. Mac Interact is an off-the-shelf round that you can use whenever you want to prepare something for the Mac. You just send like a JSON object, and all the preparations, like uploading your request to the IPFS node and preparing all the transaction and everything, is taken care automatically for you. And then once we finish this preparation, we transition into transaction settlement round, which is one of these big rounds that we also reuse constantly, because this takes care of automatically signing transaction, reaching consensus on transaction, sending it to the chain, verifying transaction, waiting for the transaction to be verified, and so on. Once we finish this, we go into a very small round, which is post-transaction decision making. This is something that you don't need to touch. It's basically something that says, all right, if we have sent a Mac request, we need to go again into Mac Interact, and if not, go into decision making again. And why do we need to go into Mac Interact as well? Because here we also have some implementation where the Mac response is decoded for you and put into a nice JSON object that you can use on decision making. So we go back into Mac Interact, everything is decoded, and then the data is sent to decision making for you. And here we are once again in decision making, but now we have a Mac request, so we already have a transaction that we can sign. Decision making knows that, so it knows it's time to settle. So it sends this new transaction to transaction settlement that once again signs the transaction, sends it to the chain, and here we hit the post decision making again, and we go back to the beginning where the loop starts again. So now the happy path is complete. Of course, all these green boxes also handle all of crazy corner cases and errors and everything. That's why it's important to have this separated and modularized code, so everyone can reuse them. And I think now I can show you a bit of the code.
Wait, can I interrupt you, because I feel like you presented so much, and like maybe it's nice to have like a tiny break and I just ask you one question before we move on, because I think that was a lot of information, and you can have a drink of water. So what I found very interesting, and what I would love to ask, and I know we still have some time, not too much, maybe you can answer it. So you were talking about these different agents, and then at registration, they kind of like connect with each other. But when I think about finding consensus about a transaction, I always think about like they need to share specific like information or the same knowledge, or also the same programming. So like how can we imagine, and then just like to iterate, so I'm kind of summarizing everything you said. You also said like you would have agents for different tasks, right? But then how, or like why could I have an agent that just does a lot of different things, or does it make sense to have agents for different tasks that then interact with each other? And how do they find this consensus on how do they share the information that is important to find this consensus?
Yeah,
it's three questions in one, but
yeah, it's a very good set of questions actually. So the way Olas agents are thought is that you basically can architect your services as you need. There is no enforcement on how many agents you need, how they need to interact. Basically, we provide this open source framework with lots of, let's say, pre-programmed use cases that you can reuse, but you can have either one, like this case. This is a simple service that just runs one agent, so consensus does not matter here because there's just one agent, right? But you can run this, you can have a service made up by, I don't know, 100 agents that run the exact same thing. Or you can have a multi-agent service made up 100 agents that do 100 different things. But depending on what you are trying to achieve, it makes sense to do one thing or another. The important thing to have in mind is that whenever you define these rounds, these steps on the flow chart, is that you need to know what your agents are supposed to reach consensus on and what not. So for example, if this is a service where all the agents do the same thing, it makes sense that they share the same information and everything is the same. For example, in a transaction, you share the transaction hash. All the agents should see the exact same hash so they can sign it, send it to the safe, and therefore the transaction is processed. Maybe you are sharing other things that are not related to a transaction, for example, a database or some usernames, something. If your agents are supposed to agree on this because your service is run by agents that run the exact same code, then you will use some classes that force all these agents to reach consensus on that. But if not, you can use other classes where basically any agent can share different data and every other agent will be fine with that. All right.
Okay.
So you are responsible for defining where we need to reach consensus and on what data and when not.
Yeah. Okay. Yeah, I will then probably be one of the most important parts of like designing this like multi.
Yeah.
Yeah.
It's
Cool.
important.
Yeah.
Yeah, it's important to have a very good idea of the architecture before you actually start coding, because sometimes you want different agents, sometimes you want the same, sometimes you are fine with just a single agent because you are the only one running it, and sometimes you want to run this in a distributed way where you run all the agents, or a decentralized way where different parties run different agents.
Yeah. A good example for that would be probably to look at the governor or something, right? Because like you have like a whole governance mechanism designed with agents agreeing on specific things. There's like 2 questions, maybe we can answer them before we move on. So one question is, are these agents meant to do tasks and execute others depending on a number of events? I think this is exactly what we talked about. This is what you need to define in the architecture. So for example, if I have an application that is meant to buy Celo depending on specific price fluctuation, is that what they do? Yeah, that's exactly what an agent could do. They could take data from an Oracle or like from Chainlink price feed, and then as soon as like Celo has reached one euro or €2, you could have like in the safe, you could have the agent buy based on like the inputs you gave by that amount. Like, you know how like on Binance you can say like, if the price reaches this, buy that much of that token. And this is what you could program your agent to do exactly.
Yeah, even that's a very good example, because oracles is one of the first things where we actually started using this. So we have this price oracle. It's similar to Chainlink, but the difference is that it happens, most of the part happens off chain. You have M agents that are observing prices in different APIs, like from Binance, from Uniswap, from CoinGecko. Different agents pulling data from different prices. They compare, they agree on the data, and when a threshold of agents agree that the price is over or under this number, then they update a smart contract on chain, so that contract can be used as a price oracle as well. Yeah.
Cool. Okay. Amazing. Okay, now up next to you, the last part, I think.
Yeah, I just want to show a bit of the code. Oops. Here. Yeah, there is this high-level part at the end of the README where we explain a bit how to extend the agent. This is the advanced part, right? So what we need to keep in mind here is to remember what I say at the beginning. Agents are split into these 2 different logical parts: the business logic and the consensus logic. For the consensus logic, I don't think we have time for that today, so I will be focusing on the business logic. I want to show a couple of methods that you can change. So let's, for example, think that we wanted to modify this agent. So instead of making a transfer, we do a swap, or we make a contract call, whatever. If we go into the packages, remember that everyone that implements any packages has their name here. So in this case, I work for Valory, so all my packages are inside Valory. You want to look into skills, and the business logic for this Celo Trader is inside Celo Trader ABCI, inside the behaviors.py file. So I open behaviors. I will also open another one, which is rounds, but I usually like to show these 2 files side by side, because on the left we have the business logic, on the right we have the consensus logic. As I said, we don't have much time for this, but just want to show one thing. This diagram that I have been talking over is defined in code here at the end of the file. Here's where we define, all right, I am in decision making. Whenever I need to go into the MEC, I transition into that other round. whenever I am in this other round and I receive the MEC event, I transition into this other. This is the way we specify this kind of diagrams with FSM apps. But the funny part is on the on the left hand of the screen. So each of these boxes, each of these rounds have what we call a behavior class. So the decision-making round has this decision-making behavior where all these decisions are being taken. This is the most important method here, which is called async act. So agents are constant. Whenever an agent is in state A, in this case on the decision-making state, it will be constantly calling async act method until the round is finished. So this is, as you can see, this is asynchronous programming. So another important thing to take care here, to have in mind here, is that you should not make any, library calls that are blocking, because this is supposed to be running asynchronously. That's why we are always using these yield from calls. Anyway, you don't need to take to do any changes to this async tag, because all this method does at the moment is to call get payload data. The naming is not important at the moment, but here is where basically we do things like, if, for example, we get some user request, if we have user requests, we prepare some data and we return it. This data is responsible for telling the agent, should you transact to the MEC interact or to transaction settlement or whatever. Basically, going back to the diagram, we are here. This is where we are preparing the data, so we can go this path or wherever we are in this round, we go to the right or to the left. For simplicity, and since we don't have a lot of time, the most, I think, interesting part is whenever you build a transaction. So this is where pill safe transaction hash comes into play. In this framework, we don't directly use libraries like Web3Py. We use it on the background, but whenever we want to interact with a contract, we first need to wrap that contract around what we call a contract packages. This is because since this is, like I was saying, this is some framework that runs everything in the background. So contracts, different packages, all this business logic is in a different package, and all of them are communicating with each other using messages. So we use this kind of structure that basically creates a message to these other packages. For example, in this case, I am making a contract call, and I'm saying, okay, I want to send a message to the contract package that handles that contract calls. So I am going to call this method of the contract, and I'm going to send this data and these other parameters. For example, if you have a contract call that implements a method called dummy method and that receives some dummy data, you should be doing something like dummy method, and then you should be sending all your parameters like this. It is a bit weird at the beginning, but this is how it works with Open Autonomy Framework. And even if it looks a little bit clunky the first time you see this, it provides a very powerful backend to do all sort of crazy things. So remember that any contract call that you make needs to go through a safe. So you actually need to prepare first the transaction itself and then wrap it around a contract call for the safe. So it's like a call inside a call. For this, I have provided a link at the end of the repository. Let me go to README once again, just in case we run out of time. There's a few steps here and some pointer on what are the most interesting methods that you should change if you want, for example, turn this into a swap. But there's here a link. Here's a contract method for reference. And this actually points to another repository, which is this price oracle that I mentioned before. This is a very big function that makes a complex contract call. The first thing it does, remember, this has nothing to do, this is just for reference, this has nothing to do with our agent. This is just another agent that prepares some safe transaction to call, to make a contract call. So the first thing it does, it just makes a read call. So it gets some data from the chain. Once you have verified that there's no error in your read call, you get some, again, this is not important, but you get some data from your response. And now things get interesting, because this is where you actually first call this contract, which is off-chain aggregator contract.
David, could you zoom in a little bit? Because right now it's like, I think that's the most interesting part. So that would be great.
I lost it. Sorry, it was online. But let me open it again because I lost the line. Yeah, there we go, transmit. Can you see it now? Oh, it's not this one. Let me... Where was it? I lost it. Send data to server. There you go. Yeah. So here it is. We are now calling off-chain aggregator contract. We are calling the get transmit the transmit data method, and we are passing these three parameters. And once we get the response message back, we always check whether there have been any errors when we do one of these calls. At this point, we know that there's no error, and we get the data of that transaction back. So this was the first step, which is prepare the transaction hash, right? And now we do an extra call to wrap that transaction around a safe call. Remember that agents do not use their private keys to actually make transaction, but to sign safe transactions. So here we call the Nosy safe contract. We call the transaction hash method. We send some data, and now we have wrapped the original contract transaction around a safe transaction. And now we are in the position where we actually can send the transaction. All that we get is the safe transaction hash. And then you can forget about everything, because if we go back to the diagram, we are at this point, we just prepare transaction hash, and then we transition into transaction settlement, and transaction settlement takes care of everything, signing and mining everything for you. So it's not like you need to actually send the transaction, you just need to prepare it, right? That's something that I need to everyone to remember. I don't think we have much more time. Maybe Lena, you have some questions, or maybe
I have two questions. So, like, one question is from the audience, which says, "Is Tendermint necessary for all agents?"
Sorry,
yes.
What
is Tendermint? It was from the beginning when you explained all the setup, the requirements for like using an agent, and it said you have to use Tendermint, and then somebody asked, "Is Tendermint? Do you have to have it installed to use an agent?"
Yes. Tendermint, even for this case, since we are using open autonomy, we usually, it's a requirement if you are running a single agent, because that's how the framework implementing. You can not use it, but you need to have it installed. This is why it's here on the.
You just need to have it installed on your machine, and then it will be called whenever it's needed. My next question is, so you talked about, like, right now you showed how I do a contract call, but for example, when I'm as a front-end developer, when I do a contract call, I need to like first, like my smart contract will be kind of translated into an ABI, into a JSON file, and then I can call the smart contract function. What do I need to do to prepare like my smart contract so I can call it from the trader agent?
I actually forgot about that. It was on my notes, but happily you remembered. So let's say, for example, I want to make a call to NosiSafe.
Yeah.
So in this list of files here, you will see that there's a folder called contracts. And this is what, when I said contract packages or contract wrappers are for. So if I go, for example, to NosiSafe contract, there's this Python file. This is the wrapper I was talking about earlier. This is usually can be as simple as a single method like this one. So you need
if I just want to call the one, I can just put in the one.
Yeah. Okay. You only need whatever you want to call. If you want to call, for example, this method is calling, I don't know, deploy transaction or something. This is where things look more familiar, because this on the back uses Web3 Pi.
Yeah.
So it's a matter of just preparing the transaction here and returning the transaction preparation. That's it. You need to implement one of these contract packages and then call it from the behavior side.
So me, as somebody who has not yet used, what's the framework called again? The Web3 Pi. It's just a Web3 library to call smart contracts, right? So like I would have to look into how to use that library to call the smart contract.
Well, this is the Open Autonomy framework, which is the framework that we use to develop Olas agents. And in the back, it uses Web3 Pi, but you should use and follow the syntax from one of the other contracts. I provide some links on the README, so you can use other contracts for reference.
Okay. Yeah. No, because I'm trying to understand like how, if there's like an official, compiler already for like Solidity to the open, I forgot.
Open Autonomy, yeah.
Well, autonomy, this looks like kind of just like the contract, somebody could build a compiler to create these files, or like
totally. And that would be very interesting. But remember that this is not an actual contract; it's just a wrapper around it. We use the ABI, and then we use Web3 Pi to actually prepare the transaction. But here it's just a simple wrapper.
Okay, so like how I would so you also use the ABI, like
If I go look at this, this contract here has a build folder, and inside the build folder there's this JSON file that includes the ABI there.
Yeah, cool. Yeah, I think that was also my question. Okay, cool. Yeah, I think that I now know how to build an agent.
Nice. Hopefully, yes, and let's see some nice agents running out there.
Yeah, I think that would be amazing. For everybody who's in the audience, if you have a question, please feel free to drop it in now. Let me just I think we went to the question how to modify the agent. You explained that, and it's also in the bottom of the README file of this repository. And to implement the agent, it's just a HTTP request. So you would just like run your agent on whatever server and then have to like call it, right? So
yeah, exactly.
Okay. My next question is like, we will share all the resources for you afterwards in an email. But also you will find the resources on the hackathon page. And you can rewatch this YouTube video, and you can also check out the Olas documentation. But you will receive an email afterwards with all the links to what we've talked about, and also the specific files. Also in the YouTube video description, you'll find all the resources also to the specific files. And please reach out for support. Also, David, maybe you want to share your Twitter in case I think a lot of people might get stuck at one point. Can they reach out to you? How is the best way to reach you in case they get stuck?
Either on Twitter or even better on Olas Discord. I usually am the one on the dev support channel. Usually I'm spending my day taking questions there.
Okay. Cool. Can you share the link to the Olas Discord here for everyone?
Sure. 1 second.
So somebody asked, this is complete in Python. Yes, this is completely in Python.
Completely.
To work with that, how will you integrate it with MiniPay? So imagine you would to integrate this, it would be useful for you to have a backend developer. You can just imagine it like any other API that you can integrate with, right? You have to host that agent on a specific server, and for testing you could, and then you will send a request to that agent, like any normal HTTP request, right? When you say get this and this or post something, this is how you can interact with the agent, like any other service or API. It's just super simple. If you have no backend knowledge, let me know. Also, I will share a file later, so in case you're still looking for a developer, when are we getting Java? Because blessing. No, I mean, I hope you have a backend developer who just can create this API simple connection for you of doing this call to the server, right? In case you don't have that, just ask ChatGPT how to create a simple API request, and then look where you could host the agent. So you can. It's not two different individual projects. So it's kind of like backend and front end. Like if you have the front end, you also have it in a different folder, but still in the same repository, right? And then you have from the agent, it's just like a simple endpoint that you can talk to. And your agent, you would host somewhere else than your front end. You can even run your agent locally. And how we did it with MiniPay, when you deploy it with the ng-rock, you could even create like a little tunnel with that. But of course, that's not really sustainable, and you should host for local deployment, for testing, for the hackathon. You don't want to waste time with hosting something somewhere. But David, do you have any recommendation where to host an agent, where people normally do that?
It depends on the resources each one has. You can run it locally in your laptop. I sometimes do that. In my case, I also like to run it on one of my servers. I usually, some people usually also rents AWS space for that, but it's okay if you run it on your local machine for this hackathon.
My recommendation for this hackathon is don't waste time in deploying the agent on AWS. Yeah. You don't have the time. You want to focus on actually building cool things. So really locally you have your port 8000, and then you can send a simple HTTP request to your port 8000, and ChatGPT will help you. Also, please, Olas is not available on testnet. You will have to reach out in case you don't have any Celo. Reach out to me and I will send you. As you could see, you normally pay 0.00 something. So I will probably send you 0.05 Celo, so 5 cents in Celo, and that will be enough to deploy smart contracts and do transactions. So if you want to integrate Olas, you will have to deploy on mainnet. Also, everybody, in case you haven't done it yet, please join this Telegram group. It's where you reach us the fastest, and where can I ask the community questions. I know a lot of you are not very comfortable with Discord, so the link above is for Discord. Please also join there, and you can reach us there. Yes, there's a minimum wallet balance because you need to have enough tokens to be able to pay gas fees and also deploy the safe wallet. So I think for the safe wallet, it's 0.004525. It's very low. And as I said, My name is Gigahertz. You can find me on Telegram and on Discord and reach out, and I will send you a tiny amount of Celo. Yeah, I think, let me just see if we have more. Yeah, just check out developer docs. Make sure you check out the hackathon. As you can see here, you can reach me as Gigahertz on Twitter, and also follow Celo Devs for all updates on this hackathon on Twitter. One Celo is far more, definitely enough. You will not spend one Celo on these agents and on deploying your smart contracts. So yeah. As I said, very cheap fees. It's amazing. Yeah, I hope you all learned a lot. I learned a lot. I feel like, of course, I think especially if you modify the agent, you might run into some questions. So feel free to reach out to David V in the Olas Discord. I will share the link with you again after this meeting, and then you can. But yeah, I mean, I would recommend to try it out. I think it's very fun. Start by trying to implement the agent, just interacting with it. I already did it today. It was exciting and it worked, and it was really cool. And yeah, so definitely get started. And if you don't know how to do it, you probably have a Python developer friend that you can make join you in your team for this weekend to make the agent work, because I think autonomous agents are fun for everyone. So like I think it's easy to convince any Python developer to get into it and just have fun with playing around with it. So recommend this video and this hackathon, and I wish all of you happy building. David, thank you so much for joining. It was great as always. Looking forward to learning much more. And then I wish everyone a great evening and happy hacking. Bye bye.
Happy hacking, everyone. Bye bye.